Hello, everyone, and thanks for joining second to the last CIIR talks of the semester. Um, I'm very happy to host Professor Jian-Yun Nie from University of Montreal. Jian-Yun is a professor of computer science and operations research. He's also the Canada Chair for Natural Language Processing and Applications. Um, his work focuses on a wide range of applications in IR and NLP, from cross-language and multilingual information retrieval to recommender systems to conversational systems and dialogue systems. He is currently associate editor of 3 journals and has served as general chairs, PC chairs, local organization chairs for multiple CIIR conferences. Um, and It's worth mentioning that he has won a Best Paper Award from CIIR and a Test of Time Honorable Mention Award from CIIR as well. He is also a member of the ACM CIIR Academy. Today, Jian-Yun want to talk about towards conversational interactive IR. So I think I should stop here, and without further ado, let's welcome Jian-Yun to UMass.
Thank you very much, Ahmed. It is really a pleasure to talk to you, to CIIR people, and I always wanted to come visit you, and I thought that this talk will be on-site talk, but finally we will do that on Zoom, and hope next time I will visit you in person. As Hamad said, I worked on many different topics in information retrieval, and the most recent topic is on conversational IR. So I'm going to talk about a few recent studies on this topic. We will see where we are heading to in conversational and interactive IR. So let me give a short definition of that. I'm not sure that everyone is familiar with the conversational IR. So let me start with this definition, which is given in the book of Gao and all last year. So it is said a conversational IR system is an information retrieval system with a conversational interface that allows users to interact with the system to seek information via multi-turn conversations of natural language in spoken or written form. And this draws a picture of what we have in mind in conversational IR. And of course, we can uh, think about the potential utilization of a conversational IR. Just to think about the smart devices such as the Siri or smartphone or any other devices that are more and more popular now. So we can imagine that in the future, we will have more such conversational interface to search information on the web or elsewhere. So that's the definition. Now, let me start with a simple example. Suppose that we have the first question, what are the main breeds of goat? And then followed by the second one, tell me about the Boer goats. And then the last one is what breed is good for meat. And here, when we talk about breed, in the conversation context, we have in mind that the breed is a breed of a goat. But this is not mentioned in the last query. So there is a need to relate this last query to the previous conversation context. So that's the need for conversational IR, one of the needs. Now, suppose that we submit those queries to Google. We can imagine that the first query will get very good results about the different breeds of goat. And then about the Boer goats, the result is also good. And the last one is somehow problematic. So when we ask what the breed is good for meat, then we see a lot of chicken breeds, not goat. And this is just one example to show that currently on Google, the current query is not related to the previous ones, even though we have a series of queries submitted to Google. And by the way, in IR literature, the committee worked on session-based information retrieval, where the last query could be related to the previous query in the session. But this has not been widely integrated in the current search engines like Google. Now you can say, well, what is the problem of conversational IR? So we have this traditional IR interface where we have independent queries. Now we have this example of conversational IR where we want to complete the last query by adding the missing concept, the missing entity goat into the query. And this is what we call the decontextualized query, which could be submitted to any search engine afterwards. So in a narrow way, the problem of conversational IR is that we have a series of conversation context, which could be a series of interactions between users and the system. For example, a series of queries, QK, and potentially we may have responses from the system, RK, in each turn. And in the last turn, we have a current query, QN, and we intend to find the relevant documents for QN. But we know that this QN could be dependent on the previous conversation context. So in a narrow sense, the one problem in this setting is to generate or reformulate the query QN into another form, QN star, and to better perform the search. So that's the goal of this setting, in this setting. So this setting is also called to reformulate the query in the conversational IR. So that's the problem that we can start with. And this problem has been investigated for several years in the IR community. So we have this cast data sets, experiments organized in track. So we can see that we have a topic and there are multiple turns, and we have those different questions in the previous turns. And we have this last one. So the purpose is to deal with the last query by incorporating the information from the previous turns. And this is the purpose of a cast. So the cast has been organized for several years. So I show 2019, 2020, and also 2021 later. We also have the data set from the NLP committee where we're interested in answering questions in the conversation setting. So one of the data sets is called QREC, which tries to rewrite the query. So here, in the first question, we don't have the rewrite, but in the second one, where we see that there is a pronoun it mentioned, which will refer to some concept mentioned in the previous question. So the rewrite will replace it by yoga in this case. So this is what we should do by an automatic rewriting process to reproduce this manual rewrite. And in the third question, again, there is a missing concept of yoga. So the goal of this rewrite is to complete the query by adding yoga. So you can see the purpose of this data set. Now, this rewriting in the conversation setting is not new now because we have the large language models already developed for some years. And we started to have this new trend of web search trying to incorporate generative AI. For example, we have a new Bing that will use GPT, but together with the Bing search. We also have a Perplexity AI, which will also generate answers by looking at the different references. So this represents, in my sense, the new trend for next generation web search, and it well, I think this trend will be um, more and more applied in the future years. So let me just show the same example by ChatGPT, and we can see that the ChatGPT is already able to answer those questions. So I submit the first question: what are the main breeds of goats? Tell me about the Boer goat and what the breed is good for meat. And we can see that ChatGPT is able to connect the breed to breed of a goat. So this seems to be easy question here. We can do the same thing with the perplexity, and the perplexity is also able to connect the breed to breed of a goat in this context. So there is no problem with that. Um, but looking at how New Bing is doing that task, and I have here some example that I get some time ago where we have this search query produced by Newbin shown on the screen. So we can see what are the search queries used by Newbin to search for documents. So for the first one, when I submit, tell me about the Boer goat, and the search query produced by Newbin is a Boer goat. And for the second one, for the last one, um, what breed is good for meat? And the search query by Newbin is best meat goat breed. And this is a reformulation by Newbin for search. And what we can notice is that um, here we have the missing concept of goat added. But this is likely a limited reformulation by Newbin, which may raise some problems later. So, but for this query, there is no problem. The Newbin can correctly deal with that. Now, what are some other examples? Suppose that I start with, are there any interesting aspect about the cow gender? Um, um, and this is Jasmine, and well, Newbin can find the relevant documents and make a summary about that. And the second question is, were any albums released? And there is a series of albums by Carl Jader. Uh, then the last question is, what were the jazz album released for? And then suddenly we notice that New Bing is disconnected from the conversation context. And the answer for that question is a very general answer of about the purpose of releasing a jazz album in general. So it is for artistic expression, for cultural impact, and so on, without connecting to a specific jazz album mentioned in the previous answer. So this is just one example to show that even though the current search engines like Newbin uses the conversation context to deal with the last query, in many cases, there may be some failure cases like this one. So the integration of a conversation context to the search is not still not perfectly done, and there is room for improvement. And this motivates the research in conversational IR. So we want to solve this kind of a problem in research. So let me just mention a few aspects of conversational IR. So conversational IR can deal with query rewriting or query reformulation, as the example shows. And we also have another family of approach that tries to develop a new encoding method for query by integrating the conversation context. And there are also a lot of work, including the work in CIIR, to ask clarification questions when the question asked by the user is ambiguous. here is one example. So suppose that the user asks, tell me about the transport in Java. And the transport in Java could be interpreted as the class transport in Java language or the transportation in Java island. So there could be a clarification question asked to the user to choose one of the meanings. There are also other aspects relating to the integration of retrieved documents into answer generation. And this is typically called the RAG, retrieval augmented generation. In my talk, I'm going to talk about the two first aspects, query reformulation and query encoding. I believe the other aspects aside, I know that many people are working on those other aspects as well. So let me just go back to the problem of query reformulation. So we have this example, and what we want is to add the missing concepts, omitted concepts back into the query. So this is the first case. And also we want to deal with anaphora. So when it is mentioned, is used in the query, it could refer to some previous concepts mentioned in the conversation. So we would like to replace it by the correct concept to make a complete query. So those processes can be well done by the large language model. So there is no difficulty to handle those problems by large language models. But what we observe is that large language models will do that in general way and not necessarily for the purpose of information retrieval. For information retrieval, there could be more useful information available in the conversation. For example, typically we can think about the query expansion by adding related information, which is not necessarily directly connected, such as the anaphora or missing omitted concept, but some information could be useful somehow implicitly. And typically in information retrieval, query expansion would add those concepts into the query to enhance the query. So this is one aspect that we can do in conversational IR. And another one is that we have some feedback from retrieval results. That is, the purpose of producing a new query is to improve search results. So we can observe whether adding some information into the query can really improve the search results. And that can be a criterion used to detect what information should be added in addition to the general query processing by large language model. So I'm going to talk about those processes. What is the useful information to use to enhance the search query? So let me just mention briefly what are the common approaches to formulate a query in the conversation context. One common approach is to concatenate all the previous queries. So when we have turns in the past, we'll just concatenate all those turns with the current query, and that will produce a relatively long query. And in the experiments, it seems that this concatenation, which is simple, in practice, it is quite effective. Another alternative is to train a rewriting model. That is, you have a query submitted by the user, and there is a rewriting model trying to transform the submitted query to a new form. So you try to transform it to enhance it in a different way. This can be done by training a rewriting model based on manually rewritten queries. In some cases, we have that, for example, in QREC dataset, as I showed. It can also be based on LLM. That is, you ask LLM to reformulate the query, or you ask LLM to reformulate a lot of queries to get a large training data. And using those training data, you will be able to train a rewriting model. Um, and there are also approaches trying to make some kind of implicit selection of elements from the previous conversation terms. So one way is to detect what are the useful terms to incorporate the inquiry expansion. And another one is to try to detect what are the useful terms. And some of the previous work try to use that in an end-to-end training so that the selection is a kind of implicit selection without the explicit signals. What we do in this first work that I'm going to present to you is about the question of what are the relevant conversation terms that are useful for the current query. So we know that not all the previous terms are useful. Um, if they are not always useful, how can we select only the useful terms to enhance the current term? So that's the problem that I'm going to talk about. And this is presented in the paper called "Learning to Relate the Previous Terms in Conversation Search." Um, and here is one example to show how a previous term may be connected to the current term. So here we have the first query, what Disney movie is Evil Queen from, and then the second one, and so on. So we can certainly ask a human annotator to annotate what is the whether a previous query is connected to the current one. So we have this manual annotation here. And for the second query, the manual annotator says that the first query is not connected. So there is no relation. And for the third query or question, the manual annotator said that the second question is related to the third query. So we have here the manual annotation. But indeed, if we try to judge whether the previous query is useful to enhance search result, then we have a different annotation, different judgment about the utility. So here we have the machine judgment according to whether the first query can enhance the second query and to improve the search result. So here we can see that for the second query, it is useful to include the Q1 to enhance Q2. And for Q3, it is useful to include Q1 instead of Q2, as the human annotator mentioned. So there is some different judgment by human annotators and by the machine according to the utility of the previous terms. So this example shows that it is not the best way to rely on a human annotation to select the previous terms to be incorporated in the current term. And instead, we have to make a different selection. And our selection here by machine should be based on the impact on the retrieval effectiveness. So this is the main idea that we use in this paper. So the hypothesis is that the conversation context is noisy, especially when it is long. Typically in the dataset Topioca, which will typically have more than 10 terms and involving topic changes. So we talk about the one topic, and then we shift to a second topic, and then it is possible to go to a third one or to go back to the first one. So there may be some topic changes during the conversation. So if we just use all the previous terms to help the current query, we will necessarily incorporate a lot of noise. So this just shows that it is necessary to select the relevant previous terms to be incorporated. So in this context, we have a limited, restricted context. That is, the conversation context is just composed of a series of previous utterances, not with the retrieved results. So we have a series of queries or questions in the history. Now we have the last question, and we want to enhance that last question somehow by incorporating the information from the conversation context. So that's the task. Now, how can we select the usable terms? So a previous term is connected to the current term if it is semantically connected. And this criterion is likely used by human judgment. So when human being annotate what is the previous term related to the current one, and this is likely the criterion used. But we can also think about the utility in a different way. So we can think of previous term to be useful if it can really help to increase retrieval effectiveness. And this will directly relate the utility of a previous term to the search task. So we will use this idea, and unfortunately, we don't have training data that indicate what is the previous term that will help to increase retrieval effectiveness. So we'll go back to some early idea developed for pseudo-relevance feedback, which tries to select expansion terms from pseudo-relevant documents. And this selection is based on a similar idea that is expansion term is useful if by adding the term into the query, we can get improved search results. So this idea has been quite commonly used in the past for traditional information retrieval. So now we reuse this idea to annotate the utility or the relevance of previous terms. And we can annotate two entities, or one is utterance, the complete utterance. So by concatenating a previous utterance with the current query, if the performance measure S is improved, then we can annotate this history HI as positive. In the same way, we can annotate the terms. Once we have the utterances or terms annotated in that way, then we can train a selector based on BERT or based on any other model. So for example, it is possible to retrain, fine-tune a retrieval model S to do the job. To be convinced that this selection is useful, I show here what's the impact of using the row query, the concatenation of all the previous queries, and by integrating the selected terms or selected terms. So here we can just look at the NDCG at 3. So in yellow, the yellow bar corresponded to the row query with no expansion. And we have the blue bar corresponding to concatenating all the previous terms together. So we can observe that there is some quite a noticeable increase in performance. But we can also look at here when we select some relevant terms, or when we select the relevant terms somehow by a selector, the performance is higher. And this shows that indeed the selection is very helpful. Now, the job is really design or to train a selector to achieve this performance. Because here we just show that when we have this annotation we just use annotated previous terms to do the job, but it is not automatic. Now, with the selection by a selector, can we achieve similar goals? So the strategy is to train a selector. So the selector can be based on BERT. It is quite easy. You have a previous turn, and you have the current turn, and you will have a BERT model that will create a different representation and then a classification afterwards. It is also possible to fine-tune the ANS model to determine the similarity between the current query and a previous query, and to determine whether we have to assign a high score or low score, and based on that, we can select the previous terms. And finally, we have this training loss to try to fine-tune what this ANS model should be trained on. And this is a loss that we can incorporate in the training process. I'm going to go fast. So we have this first module that will make the pseudo annotation. And then the second one will train the selector. And finally, we have potentially a training process that use multitask selection, multitask training for to train the selector and the retriever together. But this is not so effective at the end. So the main message is here we have a pseudo annotation, and based on that, we'll train the selectors to select the previous turns. And we tested that on several data sets, Topioca, QREC, and also some CAST data sets. So those are the statistics. We have quite some training data in Topioca and the QREC, but we don't have that in CAST data sets, or just very limited training data. Now, about the results. So we can pair with some typical baselines, no expansion, the QRETEC, which is a method trying to select expansion terms from the previous turns. So the idea of this method is that we compare the terms in the previous turns with the relevant document to see whether a term appears in the relevant document. If it appears, then we can annotate this term as positive. So this is the way to generate the training signals. And then there is a term annotation model trained based on those annotations. So the idea is somehow similar, but here we have not only the signal about the overlap of terms between relevant document and the previous terms, but we really test the effectiveness in retrieval using the previous term or previous terms. And then we have this expansion method, expand all with all the previous terms, and with relevant, the relevant terms are notated by human beings. So this is only available in Topioca dataset. And we can also train a query rewriter model. So in this case, it's a T5 model trying to transform the current query into a different form with the information of the previous turns as context information. And we have this model trying to select the previous turns. And as we can observe here, the method that we proposed here can outperform the previous one, and the previous one seems to produce quite a good result by query rewriter in Topioca, or by expanding with all the previous turns in QREC. But in our case, we show that some selection is really useful. And the last line shows the Oracle performance by trying to really use the useful previous terms. And this is the upper bound that we could achieve if the selector is perfect. But unfortunately, the selector is not perfect, so we observe some difference between what we obtained and the Oracle performance. And when we test on cast data sets, so here are some of the results. So we have different other baseline methods. ANS-conv-DR is a fine-tuned ANS model based on the conversation data set. Query rewriter is the same, and the QREC tech, as I mentioned, that's the same, and conv-DR. Again, that's dense retriever trained on some specific conversational data. ZCO is zero shot dense retriever based on Colbert. And what we can see that, again, using some selection of the previous terms, we can achieve quite good results, not as so different from the previous methods as in Topioca and QREC, but still we can see that in some cases we improve the performance, and in some other cases the performance is quite close. That's the case of CAS 20. And again, looking at the Oracle performance, we created, one of the students notated manually what are the related previous terms in the CAS 19 and CAS 20 data set. So using this manual annotation, we can get this performance measures. But if we try to make the selection, according to whether the previous term is useful, can improve the retrieval performance, we can get higher performance. And this again shows that the manual annotation can help, certainly, but it's not the best way to determine the previous tense. And this automatic annotation may create better results. Just to show you whether the previous terms are really useful. So here, if we look at the utility of different previous terms, on average, we can see that in the QREC data set, well, once we have several terms further, the utility of those previous terms is very largely reduced, but still we expect about 6% of previous terms beyond 7 turns till 11, 12. But for Topioca, we can see that the utility is higher somehow. That will be around the 10%, even beyond 20 turns. And so the utility of the previous turns really depend on the conversation context, depending on how the conversation will go on. So the difference between those two data sets is that the QREC is around the same topic. So the user is supposed to talk about the same topic, about the different aspects of the same topic. And so here the previous terms may be helpful for search or not, but usually when we talk about the different aspects in the current term, the previous terms may be related to other aspects that are not so useful for the current term. But in Topioca, there are many returning to the previous topics. So some topic that we mentioned 10 turns before can be taken again in the current term. So this is potentially why the previous terms are more useful in this tapioca data set. But I believe that the tapioca correspond more to the real conversation situation. That is, we have a free discussion, we discuss about the different topics, and it is possible that in the discussion, we'll go back to the topic of many turns ago. So this same idea has been incorporated in some follow-up study. So in the work that I just described, we only considered the previous queries or previous utterances. But indeed, in the real situation, we may have the search results, we may have the relevant passages to the previous terms. So the same question arises: how to incorporate the retrieval results of the previous terms in query reformulation. And again, we use this idea of pseudo relevance annotation to determine what previous the results of the previous terms are useful for the current term. And this again is shown to help improve the search results. So this is about the pseudo annotation of relevance of previous terms. Now I'm going to go quickly about what we can do to create a query representation. So instead of rewriting a query and to submit it to a search engine, can we create some representation for the conversation query? And can we incorporate other signals for supervision to create this representation? So the representation of query, typically we can imagine that a dense retriever would create a BERT representation for the passage or the document. And we will also have a BERT representation for the query. And we can use the training data to train those BERT representations. But now in the conversation context, can we fine-tune this query representation to incorporate the conversation context and other potential signals that can help? So that's what we will do here. So it is trying to fine-tune a dense retriever. So typically we call the conversational dense retriever. This picture will show different approaches to do that. So we have the first schema showing how we rewrite the query. That is, we have a query and we just reformulate that and submit it to a search engine. We may have the second one trying to create an internal representation of the query by incorporating some ranking signals, for example, whether the representation can help retrieve relevant documents. So the retrieval results can be used to adjust the query representation process. We have this one that I'm going to present. That is, in addition to the ranking signals based on the search results, we may also have other signals. And one typical signal is that we may have the rewritten query in the training data. So can we use the rewritten query as an additional signal to try to train the query representation? The model is relatively simple. So it is composed of several components. The basic one is to use the retrieval results, positive documents, negative documents, to fine-tune the query representation. But we will try to incorporate those two additional elements. So one is to align with the rewritten query. That is, we try to create a session query representation, which will be used for search by minimizing the distance not only with the positive document, but also with the rewritten query. And suppose that we have a manually rewritten query, and this can be used as a supervision signal. And we also incorporated a step of a selection of hard examples. That is, we want to be close to the relevant document, but far away from the hard negative documents. Again, here we can observe that this approach is quite useful compared to other approaches that use one of the criteria. So we may have a query rewriting based on only the human rewritten queries. We may have approaches that use retrieve the results, positive or negative, to fine-tune a retrieval. But here, when we incorporate um, all those criteria, we obtain better results. What is interesting to observe here is those two cases. The first block corresponds to query rewriting or reformulation, and the second block corresponds to train a query representation model, query encoder. And what we can observe is that globally, we have a better performance using CDR than using CQR. So that's interesting, suggesting that when we directly work on query representation that will be used for search, it is a more direct impact on the final search than just creating a query and then let the search engine to use it as it can. Uh, so that's some interesting observation. And also on cast data sets, we have similar results. So we have this OOD case. OOD means that we fine-tune the query encoding process using a different data set. In this case, is Tokyo, and then just apply to the cast data set. And we obtain quite good performance measures here. Um, and in contrast, when we try to fine tune on two of the data sets, cast data sets, and just test on the third one, the results is not as good as OOD case. And this possibly is related to the amount of training data. That is, we have a very limited training queries in those data sets. So using a limited amount of training data, it is insufficient to fine-tune the query encoder. So we have to increase the amount of training data. And this will lead to my last part of the talk, which is trying to help generating more training data using LLM. Um, and well, I just presented that we want to train a dense retriever based on IR dataset, and typically ANS or DPR are trained on the IR datasets. Now, it is possible to fine-tune that on a conversational IR dataset. And unfortunately, we don't have a lot of such training data. So the idea is to generate more data for the training purpose using large language models. And it is also possible to ask large language models to generate a potential answer. And this has been found to be a useful signal for the fine-tuning process. Now, the LLMs have been really used extensively for IR, for other tasks. So I just mentioned a few utilizations of LLM. So it can LLM can be used to rewrite the queries, to evaluate the relevance of a passage with respect to a query, or to generate the training data. So for example, Converser is a model that tries to generate a conversation. So we start with the first first the turn, and then there are follow-up turns generated by large language models. And we also have this generation of the query from the document or the reverse that may help create more training data. And we also have a lot of work trying to generate potential answers from a question. So those approaches have been extensively used. Now, what we do here is to look at the two possible generation. One is to create a new session completely by LLM by giving a topic to LLM, asking LLM to generate possible conversation turns between the system and the user. And another one is to generate additional query formulations automatically. So it is a paraphrasing. And we use pseudo feedback documents to determine, what is a good generation or what is a good results or not. Here is a picture of what is done here. So we have a corpus and we determine a topic, and then we ask LLM to generate the conversation around that topic. So we may have several rounds of conversation generated completely by LLM. Or we can say we have already some questions or queries, and we ask LLM to generate different formulations of the same query. And this will enhance the existing data set by adding more query expressions. And also we have this pseudo relevance feedback that we will incorporate in the generation process. And finally, the fine-tuning process will use those generated data to train a query encoder. And we hope that the new query encoder will perform better than the original query encoder in an existing dense retriever. So that's the way that we do this work. And here are two examples of the generation process. So we select the topic, and we ask LLM to generate a complete conversation. So we have the query and then the answer generated as well by LLM and the follow-up queries and so on. And we can also ask LLM to generate additional formulation of the query. So here we have input query, and we ask LLM to just generate a few alternative formulation of the same query. Now, in terms of experiments, we have tested on cast. So we again compared with the other methods. Now, this method will generate this number of turns. So we can notice that it is much smaller than what the converser used, but we could obtain quite good results for the track cast data sets. Now, using the query level augmentation, so we augment. This is the initial training data in cast 19 dataset, but we increase to this number. We can see that we have some positive impact by increasing the alternative query expressions. Now, when we try to test on Topeka, we can see that when we use the generated terms, we can obtain quite a large improvement compared to the baselines. Now, we can also look at the query level augmentation, that is to generate additional query expressions. And this does not seem to be as effective as the dialogue level generation. Now we compare with the methods using the existing data set, the training data set. That is, Topeka has already quite a large amount of number of turns, and we use that for training, for fine tuning. this is what we can obtain with this number of terms manually generated. And we can observe that with automatically generated terms, we can get closer, quite close to the performance that we can get with the manual training data. And this is just shows that it is possible that we can generate a very usable training data that could match the manual training data. And this is what we expect with LLM. So that's about it. And I'm quite out of time. And what we can observe from this some work presented in that, well, we see that the previous conversation turns may or may not be related. So it is necessary to do some selection to incorporate the previous turns into the current query. And in general, it is better to encode the query by incorporating the usable information into the encoding process instead of producing a query reformulation only. And we showed that it is usable to leverage multiple signals for training. We also see that when we have more training data, it's better. And we can use LLM to generate those additional training data. So that's the general observation that we can make. Now, just 2 minutes talking about what is the future of conversational IR. Well, there are many studies on conversational IR that relate different topics: query rewriting, fine-tuning, query encoder, asking clarification questions, and so on, many different topics. Then another topic which could be very interesting in the future, which has not been so much investigated, is how to integrate the search into the general conversation. That is, in the current setting, in the experiments, we always imagine that our goal is to do search. But this is not the general goal in general conversation. We may have a free conversation, and suddenly at some turn, we may have this search intent. And a related problem is how can we detect the search intent in a free conversation? And there are some work on that, but not extensively. And also there is a question of in the conversation or in generation by LLM, is it necessary to perform search to answer a question? And this is observed by on the fact that LLMs can already answer many questions alone without additional documents retrieved from a data set. So now the question is that when should we retrieve documents to help language models to answer the question? And this is related to the detection of LLM's confidence about the question and related to hallucinations produced by LLM. So we expect that retrieving more documents will help alleviate the problem of hallucination, but we have to detect when a language model will hallucinate. And this, there are many studies about that, but it is not yet integrated in conversational IR. And also we have to ask the question, what is the best pieces of information that we have to retrieve? And typically we just retrieve passages. Would it be better to retrieve just a few sentences instead of passages? And this again is a problem that has not been extensively investigated. And now, once the document or some documents are retrieved, how can we incorporate the retrieved information with the LLM in the generation process? Typically, we just rely on LLM to say we just create a prompt asking LLM to read the documents, and LLM can incorporate the relevant information automatically. But I'm not sure that this is really the case. And there are not so many studies trying to look at the way to incorporate the retrieve the information in the generation process of LLM. So that's another problem that we have to investigate. And finally, I just talked about the conversational IR. But indeed, the conversational IR is just one special case of interactive IR. And in interactions with the users, we may have a lot of other signals. And typically
Sorry for the interrupt. This is Hamed. We are already about 3 minutes over time.
yeah, I'm finishing here.
Sure.
So that's the last slide. So another potential future direction is to look at the broadly what is the interactive IR, not just looking at the conversation. So that's all. I'm sorry for the timing.
No worries. Thank you so much. So I don't think we have time for question answering, but a lot of students have meetings with you afterwards. So and also faculty. So I think we will ask our questions during our one-on-one meetings. So thank you so much. Let's thank Jian.
Okay, good. See you.
Really appreciate it. It was a very interesting talk, and we'll talk more about it. So we'll join the other Zoom link in a couple of minutes once we kind of go upstairs. Thank you so much.
All right.